Boxcars. What are the odds I'll roll a pair of sixes again? Six. Not this time. How can we make sense out of the seemingly random results of throwing a pair of dice, or even the haphazard flow of heavy traffic in the city? How can we talk meaningfully about any situation that is unpredictable or has an uncertain outcome? Well, welcome to the mathematics of probability.
Boxcars. My point, my roll.
Yeah, you're right, Mr. Jerry. You're one lucky guy.
No, my friend. Really, luck has nothing to do with this. These dice, they love me.
Okay, sure, whatever. You're up 3-1, so.
Oh, yes, and as we agreed, the first one to 4 points wins it all. Which means, odds are, I'm about to win.
Right.
Hard 8, so roll again.
Open up in there.
The police? I thought you said this game was protected.
Hey, what are you doing there?
I'm taking my half. I'm out of here.
What? No, wait a second here. I was winning this.
Game's over.
I said open up.
Talk about a situation with an uncertain outcome. Ancient people believed that randomness and chance were the work of the gods, and in some cultures they cast dice to answer questions of inheritance. In others, they actually chose their rulers in this random fashion. But despite the fact that chance has been a part of life from the beginning of time, it wasn't until the 1600s that the idea of chance was seriously considered in mathematical circles. There it becomes the subject of probability. The study of probability was born on the gaming tables, and in particular with games of dice. Dice go back thousands of years. Now these early dice were made from the bones of animals, often the knuckle bones of sheep, from which we get that phrase, roll dem bones. The knuckle bones approximate a mathematical shape that's called a tetrahedron, a four-sided solid object, so that these early dice were often four-sided as opposed to the six-sided cubes that we usually see today. Of course, animal bones are not perfectly regular objects like perfect tetrahedrons or the perfect cube, so you might have thought that the Egyptians, who were fairly sophisticated both scientifically and mathematically, would begin to notice that generally some sides came up more than others and that you might be able to quantify this and also win a few more bets. But instead, it was centuries later in the consideration of games involving fair dice, that is, dice where it's equally likely that each side will come up, where probability first appeared. Now, one of the first to record mathematical ideas about probability was Girolamo Cardano. Cardano was a 16th century Italian doctor, an eccentric and a genius mathematician, famous for his skills in solving algebraic equations. Cardano was also a compulsive gambler. The combination of a keen mathematical mind and a taste for the gaming tables made probability a natural interest, and his book, Liber de Ludo, contains many of the basic ideas of probability. Almost a century later, Blaise Pascal and Pierre de Fermat expanded on Cardano's thinking, and they came up with a method to actually calculate probabilities. Fermat is probably best known for the famous Fermat's last theorem, a simple-to-state problem about a generalization of the Pythagorean theorem that took the world of mathematics 350 years to solve. His day job was as a lawyer, but his passion was mathematics and physics. Pascal was the son of a tax collector, and to help his father, he invented the first digital calculator. His deep interests were in both philosophy and mathematics. Together, Fermat and Pascal were widely regarded as two of the most powerful mathematical intellects of their time. Although they never met, in 1654 they exchanged a series of letters that most academics today agree was the foundation for the modern theory of probability. Their correspondence started after a friend, the gambler Chevalier de Mere, called upon Pascal to get help with a nagging problem. De Mere asked, how would two gamblers fairly split the pot if their game was interrupted before being played to the finish? This became the famous problem of points. Until Fermat and Pascal took it on, the various solutions that had been proposed had been pretty unsatisfactory. In their correspondence, Fermat and Pascal addressed the problem by considering all the possible future plays of the game. By assuming them all to be equally likely, we can compute how much each person deserves when the game is interrupted, like for Jerry and Aldo.
I said open up.
Go ahead, let him in. Awful nice of you to stop by.
Hello, Jerry. How come you didn't answer the door? I heard you had a game going. I wasn't invited?
Well, we were, but, hey, you know that Aldo guy?
Yeah.
Well, I was on a roll, and, he took half the pot and he left.
Really?
Yeah.
Well, he kind of gotten far. So, what happened? Exactly.
Well, it was me and Aldo, a private game. We each lay down $500, and the first 1 to 4 points wins it all. Okay, so 7 gets you a point. Snake Eyes boxcars minus a point. I was up 3 to 1.
And?
And I had just rolled a hard 8. Was just about to roll the come out, and he thought you were the cops. He grabbed half the pot and he was gone.
Well, it seems to me, other than not inviting me to your little game, that what you have here is a simple problem of points.
Yeah, that's what I was saying.
Not the points you have, the points you could have. You only needed 1 point to win. Aldo needed 3. Now, if we examine all the possibilities, had the games been played out... pardon me, sir. Now, follow along. 3 being the minimum number of games that would give you an equal chance for both of you guys to potentially win the whole pot, assuming each of you has a 50-50 chance of winning or losing each roll.
I got it. Each of these branches is one way the rounds could go. If I win the first, it's over.
Right.
Aldo has to win the first, the second, and the third round.
And that means you have 7 ways to win. Aldo only has 1. Which means, to be fair and just, you're due 7/8 of the pot, and Aldo's due 1/8.
I knew it. The cheater.
Hey, Mr. Ray. Nice evening.
Aldo, you came back to see me. You, my friend, have a problem of points.
A problem with points?
Wonder what the odds are Aldo's going to come out of this with any money at all? Let's go ask Risa D'Souza, professor at the University of California at Davis. Not yet. Hi, Risa. Thanks for coming. I hope we can clear up the confusion that we saw with Aldo and Jerry. I have a feeling Jerry's getting the short end of the stick in this deal. Is that right?
Definitely. And to understand how to clear up the confusion, we're going to have to go back in time, back to the 17th century.
So Fermat and Pascal were trading these letters back and forth, effectively trying to understand how to fairly divide the pot in a game of chance that had been interrupted. So Aldo and Jerry are in the same situation, I guess. So now we know that Jerry has 3 points, Aldo has 1, and there's a 50-50 chance at every roll now that either one of them will win. Is that right?
Exactly. So now we have to go forward and iterate all possible outcomes. So what we're going to use is going back to the pizza box and look at the tree graph, which lets us calculate all the possible outcomes of a game.
So the entire future is on Ray's pizza box over there, is that right?
Exactly. So Jerry wins in 7 possible futures, and Aldo only wins in 1 possible future.
Right.
So to split the pot fairly...
Right. 7/8 for Jerry seems right, and 1/8 for Aldo.
Exactly.
A problem with points?
That's what I said.
Yeah, you cheated. I knew it. Ray proved it.
But Mr. Ray, I was trying to get away. The police were...
That was us, dummy.
My apologies. I'm just trying to be fair and split the money in half.
Fair? Ha! You owe me 7/8 of the pot. I was winning. See?
What's this?
This is a tree chart.
Okay.
It's based on the great mathematicians, Pascal and Fermat. You heard of them, right? Huh? They worked in the field of probability. Now, had you continued to play, you would have had only 1 chance in 8 of winning the whole pot.
1 out of 8, but that's not fair. I totally...
Hey. You got a problem with my math?
Absolutely not.
Good. Because we're going to continue to play until we get a nice, normal distribution. Ante up. Come on, boys. And listen, the traffic's so bad, I might as well play a little bit myself. That's a lot of lettuce.
Well, so there's probability in action. Of course, the casinos are interested in what happens when many, many people play these games, maybe the slots, maybe something else, over and over and over again. And They, of course, want to know that in the long term, they're going to win money and we're going to lose money, actually.
Exactly. So when we looked at the game between Jerry and Aldo, that was one single game. And that was the work of Fermat and Pascal.
Right.
But we're interested in what happens when games are played over and over.
The first person to think about this was Jacob Bernoulli, and he was the first one to really think about the sort of long-term behavior. Is that right?
That's correct. And that's sort of related to something called the law of large numbers. And if we have an event that we repeat over and over, a random event, and we do it independently many, many times, we find that it's going to eventually converge to a finite number that's between 0 and 1, and we call that the probability of observing the event. So the law of large numbers basically tells us that if we do a random event, a random outcome over and over, it'll eventually converge to a well-defined probability.
So we could take a very simple example, right? We could just do coin tossing, okay? So
Definitely.
I toss a coin, and if I get heads, I get $1. If I get tails, you get $1. So if we did this 1,000,000 times, million's a pretty big number, we would expect that after 1,000,000 times, I'd get about half of them I'd win, half of them you'd win, so that we should be even.
Exactly.
Is that right?
And if you think about it, the first time we play the game, there'll only be one winner and one loser, so there'll only be one outcome. So we can't use our probability equation because the probability is 1 that it's heads or tails. But we don't converge to the 50-50 until many, many coin flips.
So if you look at the game and you look at all the possible outcomes and you look at the probability of each possible outcome as with its associated payoff, and you take that simple sum of the outcome times the fraction of times that you achieve that outcome, then you get this quantity called the mean. And the amazing fact that Bernoulli proved is that if you actually play the game a large number of times, you know, in the limit, an infinite number of times, and then you compute your average payout for a very large number.
Over that collection.
Yeah.
So what you were saying is that if we look at the tree graph and we multiply the probability of an outcome times its payoff,
Right.
and we look at all outcomes, we'll compute the mean payoff expected. And what Bernoulli showed is that we have the theoretical mean from the tree graph, and what Bernoulli showed is that if we look at a collection of games, so I'm actually going to play out a series of games,
Right.
and I'm going to calculate the average payoff over that collection of games that I've just played.
Right, so just look at how much money did I win after 1,000 games and divide that by 1,000.
And what he showed was that as the number of games becomes infinite, that average that I've calculated over that collections of games that I've just played, so it's my real payout, actually converges to the theoretical mean that I calculated from the tree graph.
Gets closer and closer and closer
So
to that ideal
that's
number.
the law of large numbers.
Right. So probability theory was born on the gaming tables hundreds of years ago, but in fact it's still important on the gaming tables today. And now we're going to go visit with Anthony Bearlocker of International Gaming Technologies to see how probability makes its way in the real world of today's casinos.